Suppose Z be the set of all integers and Z0 be the set of all non-zero integers. We have a relation R on the Cartesian product of Z with the non-zero integers, and it is defined as the ordered pair A comma B related to the ordered pair C comma D if and only if AD equals to BC for all ordered pairs A comma B and C comma D belonging to the Cartesian product of Z, the set of all integers, with the set of all non-zero integers. So our goal will be to show that the relation R is an equivalence relation on the Cartesian product of Z with Z naught. So here we have a relation R. The relation R that is defined as the ordered pair A comma B related to the ordered pair C comma D if and only if AD equals to BC. So this is given to us. We have the ordered pair A comma B related to ordered pair C comma D if and only if we have AD equals to BC for all ordered pairs A comma B and C comma D belonging to the Cartesian product of the set of integers Z with the set of non-zero integers Z naught. Okay, before proceeding, let's try to understand. So the moment we say that the ordered pair A comma B is related to C comma D, all we are doing is take the x elements at the extreme end, which is A and D in our case. So this will get multiplied and that gets equals to the product of the inner elements B and C. Okay, now to show that the given relation is a equivalence relation, we have to first make sure that the relation is reflexive, it is symmetric as well as transitive. So first what we'll do, we're going to check for reflexivity. So let's check whether if the given relation is reflexive or not. So how do we check for reflexivity? So let's quickly go through the definition. So let's say R is a relation. So R is going to be reflexive in nature if it follows the criterion. That means if and only if we have the ordered pair A comma A belonging to the relation R where the relation R is defined on the set A, where we have R on the set A and we have this element A belonging to the set A. So this is when we say that a given relation R is reflexive. Now here let us consider a single element. So let's say we have a single element and this element is actually an ordered pair that belongs to the Cartesian product of the set of integers Z with the set of non-zero integers Z naught. Then so if we consider the ordered pair A comma B belonging to the Cartesian product of Z, then A is going to belong to the set of integers Z and B is going to belong to the set of non-zero integers Z naught such that if we take the product of A with B, this is the same as taking the product of B with A. This is true because multiplication is commutative. Now what does it mean when we say that AB equals to BA? This simply means that the ordered pair A comma B is going to be related to the ordered pair B comma A, and this is going to be true for all ordered pairs A comma B belonging to the Cartesian product of Z with Z naught. Okay, so this simply tells us that the given relation R is reflexive. So this is a reflexive relation on the Cartesian product of Z with Z naught. Okay, so we have verified the first one. That means our relation R is reflexive. Now we're going to go to the next part where we will show that the given relation is symmetric. So we'll check for symmetry. Now in order to check for symmetry, we're going to consider two elements. So let those two elements be represented as ordered pairs. So we have one of the element represented by the ordered pair A comma B, and the other element is going to be C comma D, the ordered pair C comma D, and both of these elements belong to the Cartesian product of Z with Z naught. Then what does it mean when we say A comma B is related to C comma D? So that's by definition is simply telling us that AD is going to be equals to, this is telling us that AD equals to BC. Now if AD equals to BC, we can also rewrite it as BC equals to AD, means exactly the same thing, and BC can be also expressed as CB equals to AD. AD can be written as DA. The whole reason we're able to write is because of the property of commutativity of multiplication. Now CB equals to DA, can we not say that the ordered pair C comma D is related to the ordered pair A comma B? Because by definition, CD related to A comma B is simply take the product of the outer elements, that means C and B, and this is going to be equals to the product of the inner elements D and A. So that means we started out by considering the ordered pair A comma B are related to C comma D, and we are able to show that the ordered pair C comma D is related to A comma B. And this is going to be true for all. This is going to be true for all A comma B and C comma D belonging to the Cartesian product of Z with Z naught. So here we have said, so we can say that the relation R is symmetric. This is a symmetric relation on the Cartesian product of Z with Z naught. Okay, now let's go to the third one where we'll check for transitivity. Now in order to check for transitivity, we're going to consider three ordered pairs. So let those three ordered pairs be A comma B. So let A comma B be one ordered pair. Next ordered pair is going to be C comma D. And then we're going to consider one more ordered pair, E comma F. So let these three ordered pairs belong to the Cartesian product of Z with Z naught, such that A comma B, this ordered pair, is related to the ordered pair C comma D, and we have the ordered pair C comma D that is going to be related to the ordered pair E comma F. Now what does it mean? This simply means that if A comma B is related to C comma D, then can we not say that the product of the outer elements A and D, this is going to be equals to the product of the inner elements B and C? And since the ordered pair C comma D is related to E comma F, then here we can say that the product CF is going to be equals to DE. Okay, fine. Now we have two equations, AD equals to BC and CF equals to DE. So here let's do one thing. So here let's isolate C from here. So isolating C means we are going to get AD over B. So we're going to use C equals to AD over B into the second equation where we'll replace C with AD over B. So A times D over B multiplied to F, this is going to be equals to D times E. Now clearly we see that D is a common factor on both sides, so we can divide both sides with D to get rid of the factor D. So that's going to give us A times F equals to B times E. Now A times F equals to B times F, this is simply telling us that A comma B, this is going to be related to the ordered pair E comma F. So where is AF? A is simply the product of the outer elements E and F, and BE, this product B and E, is the product of the inner elements. So here we started out by considering two ordered pairs, A comma B related to C comma D, and then C comma D related to E comma F, and we are able to show that A comma B is also related to E comma F. So this is telling us that our relation R is, this relation R is transitive. This is a transitive relation. Transitive, and it is going to be transitive on the Cartesian product of Z with Z naught. Now we have successfully showed that our relation R is reflexive, it is symmetric and transitive. Hence we can say that our given relation R is an equivalence relation. R is an equivalence, it is an equivalence relation on the Cartesian product of the set of integers Z with the set of non-zero integers Z naught. Hence proof.